Hello everyone, welcome to today's video where we will be talking about topics 1.6, 1.7a, and 1.7b for AP Pre-Calculus. We will be talking about key concepts, important definitions you must know, and we'll be showing you guys examples on how to do certain problems regarding these topics. Okay, so let's start.
Topic 1.6, polynomial functions and end behavior. Some vocabulary words you need to know are end behavior, limits, and limit notation, and we will be going into how to write limit notation. End behavior is describing what is happening to the polynomial function from the very far left of the graph to the very far right of the graph. Limit is the value that the function approaches as it goes to an x value. Limit notation is a way of describing the behavior of a function at a given location. In order to write these limit notation, you have to think about where the x is going and where the y is going. So the x values are approaching negative infinity. We note that as x approaches negative infinity, p of x, our function, equals negative infinity. On the other hand, the x values are approaching positive infinity, and that will be written as x approaches positive infinity, p of x, our function, equals to positive infinity. So on the table, it's going to describe from the left side, if the arrows are going upward, then it would be the limit as x approaches negative infinity, our x values, p of x, our function, equals positive infinity, our y values. On the right side, as arrows are going upward, the limit as x approaches positive infinity, our right side x values, p of x, our function, equals positive infinity, our y values. Going down to the left side, our limit is as x approaches negative infinity, our y value, p of x, our function, equals negative infinity, our y value. Right side, going down, the limit as x approaches positive infinity, p of x equals negative infinity. And you have to note that when you say as x approaches positive or negative infinity is saying the left side of the graph. And when you say positive infinity, that is noting that you're talking about the right side of the graph. Let's fill in this phrase. If the leading term has an blank degree, the left and right side will behave blank. We know that when an even degree, both sides are going to behave the same. And with this example we have at the top, we see the leading term is 5x to the power of 6. The leading degree is 6 and it's an even degree, and that the left and right side will behave the same. Even degree and positive leading coefficient, an example of this would be p of x equals x to the second power. It would be the limit as x approaches negative infinity, the left side, p of x, our function, equals positive infinity, the y values. And for the right side, the limit as x approaches positive infinity, p of x equals positive infinity. However, this is different when the leading coefficient is negative. Hypothetically, if 5 was negative 5, the even degree and a negative leading coefficient, for example, p of x equals negative x squared, as x approaches negative infinity, p of x equals negative infinity. On the right side, the limit as x approaches positive infinity, p of x equals negative infinity. Let's fill in the blank. If the leading term has an odd degree, the left and right side will behave the opposite. So we see here that our leading term is 8x to the power of 5. We have a positive leading coefficient and a odd degree. The left side's limit is as x approaches negative infinity, p of x equals negative infinity. But it would be different with the right side because the left and right side behave the opposite. The limit as x approaches positive infinity, p of x equals positive infinity. When the odd degree and a negative leading coefficient, for example, p of x equals negative x to the power of 3, equals positive infinity. However, with the right side, since it's an odd degree and a negative leading coefficient, it will behave the opposite. So the right side is the limit as x approaches positive infinity, p of x equals negative infinity.
Okay, so for example number 1, for topic 1.6, we're going to be talking about end behavior and limit notation, which is a crucial concept to know in AP Pre-Calculus. The problem says, describe the end behavior of the function using a limit notation. So, to do this, we must follow a series of steps to get to our solution. First, we need to determine whether the leading coefficient is positive or negative. So when we look at our function, we see that the leading coefficient is 7, and it is positive, which will greatly help us to determine the end behavior. Secondly, we must determine whether the degree is odd or even, which will also help us see if the end behavior is the same or different on each side. In this question, we see that the end behavior is even, so both of these sides will be going to the same direction. I'd recommend visualizing what the graph will look like to help you answer the question. In the end, we will end up with as x goes to negative infinity, g of x will also go to negative infinity, and as x goes to infinity, g of x will go to infinity as well. Now, moving on to example number 2 of topic 1.6, we are going to be talking about a similar concept, but this time it will be in graph form. So it's all the same concepts. First, you want to look at the end behavior of the left side of the graph and determine whether it is going up or down. If it is going up forever, then it is going to be positive infinity. If you're going down, then it is going to be negative infinity. Once you have made the decision of whether it's going up or down, write it down in limit notation form. After that, you're going to look at the end behavior on the right side of the graph and determine whether it is going up or down. Again, if it is going up forever, then it is positive infinity. If it's going down forever, then it's negative infinity. Once you have determined if it's negative or positive infinity, you will write it down in limit notation form. So our final answer for this example will be as x approaches negative infinity, g of x will equal negative infinity. And as x approaches positive infinity, g of x will equal negative infinity.
Topic 1.7a, Rational Functions and End Behavior Vocabulary. Rational function. The ratio of two polynomials where the polynomial in the denominator cannot equal 0. Domain of a rational function. The set of all possible x values for which the function is defined for rational functions. This excludes any value that makes the denominator 0. Vertical asymptote. A vertical line, parentheses, x equal a, close parentheses, that the graph of a rational function approaches but never touches, occurring where the denominator equals 0 and the numerator doesn't cancel out. Horizontal asymptote. A horizontal line, parentheses, y equals b, close parentheses, that the graph approaches as x approaches positive infinity or as x approaches negative infinity. It represents the end behavior when the degrees of a numerator and denominator are the same or the denominator has a higher degree. End behavior of rational functions describes what happens to the values of f of x as x approaches positive infinity or as x approaches negative infinity. For rational functions, this depends on the degrees of the numerator and the denominator.
Okay, for the first example, we're going to figure out how to solve key features to this rational function, which is Rx equals x to the power of 3 minus x 2x squared minus 3x over x squared minus 4. So for domain, first we need to find the denominator of the rational function. After that, we need to set the denominator equal to 0 and solve for x. Afterwards, exclude the values that make the denominator 0. And lastly, write down the remaining values as the domain. For vertical asymptote, first we have to factor the denominator to find where it equals to 0. Afterwards, solve for x. Then check the numerator to ensure it's not 0. And finally, find out that the vertical asymptote is where the denominator is 0, where the numerator isn't. In this case, it will be x equals 2 and x equals negative 2. And for wholes, one thing to note is that wholes only occur when the denominator and numerator are canceled out. So the first thing to figure out the wholes is to factor out both the numerator and the denominator. Next, check for any common factors between the two. And next, figure out whether the common factors cancel out or not. So in the case of this problem, there are no wholes.
Moving on to example 2, we have this equation x squared divided by x squared minus 4. And we'll be using it to complete the table to answer the following questions. The table shows the values for x, which are negative 10,000, negative 1,000, negative 100, 100, 1,000, and 10,000. So we'll be individually inputting these values into the equation to come out with f of x. We see that f of x as it's going to the negative side is slowly increasing but not reaching 1. And as it's going to the positive, it's slowly decreasing as it's coming to 1. So we'll find that the end behavior as x is approaching negative infinity, f of x is approaching 1, and as x is approaching positive infinity, f of x is also approaching 1. To find the horizontal asymptote, we can simply see where the line doesn't touch in the table. And as you can see, from one side, from a negative 10,000, it increases to 100, but you can see the skip over 1, which we can assume is the horizontal asymptote. And for that, we'll be given the equation y equals 1.
For topic 1.7b, definitions and concepts, a rational function, a function that could be expressed as the ratio of two polynomials, and behavior, describes how a function behaves as x approaches either positive or negative infinity, horizontal asymptote, horizontal line of the graph that approaches as x approaches positive infinity or negative infinity, and limit, the value that a function approaches as the input x approaches a particular point or infinity. Limits are used to formally describe the functions and behavior.
For our first example, we have this graph which we'll be using to answer the following questions. As we can see, this graph has 3 different portions to it, so we'll have 3 different portions to our domain. We can see that the left side of the graph approaches negative 5, so from negative infinity to negative 5, we have one portion of the domain. The second portion can be seen in the middle of the graph, which is described negative 5 to 0, because we can see it's between negative 5 and 0. And the right side of the graph is described as 0 to infinity, because from 0 to infinity, we have the right side of the graph. There's no y-intercept because, as expressed by this green line, there's actually a vertical asymptote there. The limit as x approaches negative infinity is 0, because we can see the left side of the graph approaches 0 but never actually touches it. The limit as x goes to positive infinity is also 0, because like the left side, it also approaches 0 but never touches it. As x increases without bound, the f of x approaches 0, because you can see the right side, it increases. And as x decreases without bound, f of x also approaches 0, because we can see on both sides of the graph, when x decreases without bound, it also approaches 0.
This is example 2 of topic 1.7b. We see our problem on the top right. It is x squared minus 4 all over x squared minus x minus 6. We're going to take a look at the domain first. To find the domain, we need to find where the denominator is equal to 0. When we factor our denominator and we solve for that, we see that x is equal to 3 and x is also equal to negative 2. So that means we need to exclude these values from the domain as shown here. Our second step is our vertical asymptotes. Our vertical asymptotes occur where the denominator is 0 and not canceled by the numerator. we're going to factor the numerator, and we see that the factor cancels, so there's no vertical asymptote at -2. The remaining denominator factor, x minus 3, creates a vertical asymptote at x is equal to 3. So this means our vertical asymptote is x is equal to 3. We're going to see our horizontal asymptote now. We're going to compare the degrees of the numerator, which if we look here, we see that our degrees for both the numerator and the denominator are 2. So when the degrees are the same, the horizontal asymptote is y is equal to the coefficient of the numerator and the leading coefficient of the denominator divided by each other, and this means they're equal to 1. So our horizontal asymptote is equal to 1. And our last step is our holes. Holes occur when a factor cancels out in both the numerator and denominator from the factored forms. When we factor our numerator and denominator, we see that our factors cancel, creating a hole at x is equal to -2. So to find the y-coordinate of the hole, substitute x is equal to -2 into the simplified function, which is f of x is equal to x minus 2 all over x minus 3, which creates our hole at -2 and 4/5.
Okay, to end the lesson, I'm going to be telling you a couple of jokes. Number 1, how do rational functions throw a party? They just divide and conquer. Okay, how about this one? Why was the rational function nervous on its first graphing test? It was worried about its limits. Well, that concludes this lesson. I hope you guys had a good day, and bye-bye.